Hello! Welcome back to another broadcast day. My name is Relevant and welcome to Do All the Things. That was 2 welcomes, value added. On today's episode, I'm going to attempt to install a literal headlight onto my pedal bike. I'm not talking about some crap little LED dealy. I'm talking about a literal headlight. Stay tuned. I think I can pull it off. So as the story goes, maybe at least once a week, sometimes a couple times a week, I like to bike into town, to catch my dinner. Maybe I'm picking up some fast food that day, get a little bit of exercise, a little bit of cardio, a little bit of burn off those calories before I friggin' eat them. And well, quite frankly, I need to maintain some minimal physical standards. That said, it's a 20-minute ride and there is a massive uphill. So it's a fun ride. Now the thing is, I eat dinner around maybe 7 p.m. So I'm taking this trip into town around 6 p.m. and at the time of filming, it is mid-October 2021. That means it's getting dark early. By the time I have done my shopping, sometimes I'll just go do groceries. I'll be in town for an hour. It's dark. Last time I went into town, I was biking back in the dark, and because I'm just slightly outside of town, oh boy, it's like, whoa, there's this big downhill. Like, we're talking a big downhill, and there's no streetlights on this downhill. It's just like, okay, what the frick? So the bike that I have has, a couple of those little lights on it already. It's got the blinker red at the back. It's got this tiny little LED dealy in the front, and it doesn't actually light up anything. It's mostly just a marker. So, if you're inner city and you can see with the street lights, you got little blinky so the cars in the distance can see, hey, there's someone there. Let's be careful. So either way, I need more light. So you start off by hopping online, see if you can find something cheap on sale. The stuff in the price range I wanted sucked, especially those LEDs are going to be the blue, ugly blue ones. I don't like the blue ones. And the stuff I did like, it was, more money than I wanted to spend, especially considering it's October. I'm in Northern Ontario. It's probably going to snow soon, and then I'm not going to be able to use it anymore. So, you got a ROI to consider here. But I'm thinking, well, how much crap do I have around here? Maybe I could just chuck something together. And yeah, I came up with a plan. And it starts off with I pulled this thing off the back of my quad, hence a literal headlight. Like, we're gonna have a literal headlight on my bike. And because it was mounted to the quad, it already has a bar mount, and I checked it fits perfectly on my handlebar. It's gonna sit there. It's gonna look maybe a bit ugly, a little bit silly, a little bit wannabe steampunk. I don't know. Once upon a time, before LED lights got good, in the turn of the century, if you wanted some decent lighting, you still had to go with incandescent, and I actually collected quite a few of these par bulbs. The one in question I'm going to be using is this guy right here. That's 6 volts, which means I can run it easily off batteries. 8 watts. 8 watts of incandescent isn't a huge amount of power, but it's going to be just enough for a pedal bike so that I can see in front of me, especially on a familiar route. You just need to be able to see. This thing, well, you can tell it's been on a quad. It's going to need a little bit of cleaning. It's got a hole in it too. That's a bonus. We're going to have to do something about that. I think I once had a push button switch installed onto this so I could turn it on and off. Either way, it's not going to be this bulb. I think that's a 12 volt, 35 watt halogen or something like that. So how are we going to power this thing? Well, it just so happens I have a surplus of 26650 cells that I don't use that much anymore. They're for flashlights. I have all sorts of 2D flashlights over the years I've modded to take a pair of these cells. If you've heard of candle power forums, you might have some idea of the kind of crap I'm talking about. Once upon a time, any aftermarket upgrade you can imagine for a 2D mag light, it existed. You can get it on this forum. I own a few 5 megas, not gonna lie, but I don't use them that often. But either way, this isn't the most ideal for the application. If we're gonna get fancy, we wanna run it off like maybe a triplet of 18650s, but I wanna put these things to use, and I have, many of these. I can bring spare batteries, no problem with me. The only problem is, this is gonna give me 7 to 8 volts. This is only wants 6 volts. Either this pupper is gonna fry instantly, or it's not gonna live very long, so we need to control and regulate that power somehow. This is what I came up with. Wait, I took the batteries out. Oh, well, there goes my grand entrance. Okay, batteries are in. Oh, now it works. Now, it doesn't seem like a lot of light here on camera, but I tried it out in the dark. It's good enough. And what I like about it is it has what's known as a trapezoidal flood or trapezoidal spot. So, you know, it's hard to see here, but it presents a square, not a sharp dot. At about 20 to 25 feet in front of you, where I'm going to aim this thing, you end up with a square pattern with just a little bit of fall off on the side. So most of the light is focused into a nice visible chunk. Like, it's a very ideal for a headlight, especially if you don't want a bunch of spread or anything blinding people and you don't want a harsh spot. It's going to give me some nice even light out in front of me. So that's perfect. And then here's a little circuit, like, okay. Hey, doesn't that just look fancy? That or mom's spaghetti splattered on a breadboard. And we got a push button and we press it, it turns on light on, it turns light off, it turns light on, it turns light off. I like this. I've pressed this button a lot in the past day or so. So what's going on here? Well, we have a solid state switch using a momentary push button and PWM regulation, the most efficient regulation. I suppose I should explain to you how it works. I'm sure you are just waiting in bated breath for all the math and science behind what this does for the simple aspect of a headlight on my bike. Because I just kind of threw this together with parts that I had in stock instead of, like, you know, buying stuff. So yeah, our circuit comes in two parts. We're gonna split it right here. I'll explain the second part later, but the party starts over here. So here we have a good old-fashioned Smith trigger inverter. I'm using the TC4S584 by Toshiba. I really like the way these guys work as PWM drivers. So we have our power coming in. We have a 1K drop-in resistor here. I didn't do math for that. It's arbitrary. This uses so little power, it's hard to calculate. And then we have a 5.1 volt Zener diode, whose purpose in life is to clamp the voltage going to this guy, even though it's rated for 18 volts. That 5 volt clamp is going to give us a consistent frequency. Instead, if we didn't have that, the frequency would change with the battery voltage as they start to go down. At its basic, we have a relaxed oscillator, 100K feedback, 220p capacitance to ground. That gives us roughly 100 kilohertz of PWM switching speed. Now, the thing is, if we just run a 50% duty cycle, well, we're going to end up cutting our voltage in half. I think you know it. So we got to adjust on our duty cycle. For that, we use this guy right here. That's a Schottky diode, an SD103. It's a tiny little cutie like the 4148, except Schottky. You can't use a 4148. They don't switch fast enough to hit these kilohertz. They're just bling. This resistor set in our duty cycle. I do not know why this pencil is in here. It belongs in the other room. I'm using a 4.7K. So what happens is when the output is high and high is driving the circuit, it goes through this 100K, slowly charges up this capacitor before it hits the voltage threshold, and it's going to take a certain amount of time. But when it goes low, it can pass this route through this Schottky diode, and that significantly lower impedance is going to cause it to switch out of low very quickly. We end up getting a signal that looks like this, where it's mostly high with a little blip of low, and we're batting maybe 80 to 95% duty cycle. From there, it passes through a 10K buffer, resistor, whatever you want to call it, into a Mosfet gate driver. I'm using an MCP1415 inverted Mosfet gate driver. That is very important. We need an inverted driver that drives this right here, the Mosfet. The Mosfet I'm using is an Alpha Omega I21357, and it is chosen because it is one of the cheapest PNP Mosfets I could get in through-hole that had specifications that I wanted. And I didn't buy it for this circuit. These are just a couple of Mosfets that I brought into stock to try out because I'm like, oh yeah, I want a cheap Mosfet that could do things. Oh, let's try these ones. And I didn't use them for any projects. If I have a more prestigious PWM application, I have faster, more ideal MOSFETs. But it's working great in this application. We got 30 volts and a theoretical 70 amps, but really its normal rating is maybe 20 amps. Well, it's got a lot continuous drain current. Why are there two continuous drain currents? 70 amps or 23 amps? How about you make up your mind, bud? IDSM. There's probably a reason for it. Either way, it has more than enough amperage for what I'm doing here. That 8-watt bulb pulls about 1.35 amps. It supports a 4.5 volt RDS on, which means we can drive with logic level. Indeed, our gate threshold voltage is in that range, equivalent to a logic MOSFET. Our input capacitance is a bit high, but I've seen similar capacitance on MOSFETs used for more prestigious PWM applications, and it's pretty fast. 12 nanoseconds, 18 nanoseconds, but then the elephant in the room, who invited you to the party? Turn off delay time. Yeah, you are definitely slow to leave the party, bud. You're one of those guys who likes to chat a lot. Long goodbyes, this MOSFET likes to say. But fortunately at 125 nanoseconds in, your 100 kilohertz PW range, more than fast enough. Tested in this application, runs perfect. Gonna be getting more of them. We got a capacitor here, and it is basically our main for the circuit in general. It is a 100U 50 volt that I have Nichinon. Where is it? I got frickin' parts everywhere, bud. HEM, a UHE. I think it's somewhat low ESR. Either way, after testing, I found it worked best compared to even larger values, smaller values, whatever. I don't like, this is a quick and dirty PWM. I'm not an expert on designing PWM, so like I'm still hazy on the math of capacitor selection. I just kind of fire up the scope here and then I YOLO bomb caps into there until the circuit works the way I want it to and everything, the functions are all there. We put that physically as close to the MOSFET as possible because in order for a MOSFET to do its job, it has to switch on and off real fast, which means we want that capacitor to take up any inrush current. It doesn't have to pull through anything. And then of course, on the output of the MOSFET, we have ourselves a diode to work with an inductor, which according to this drawing is hooked up into the completely wrong place. Revision 2.1. You need the diode to work with the inductor, which is a 47U. What inductor am I using? Oh, I looked it up. It's a 47U, 1.5 amp rated, which is actually too small. If you are building a PWM and my calculator's dead, that's awesome. You need 1.5 times your current. So 1.5 times 1.34, I'd need a 2 amp. And indeed, I tested various inductors in here. I could get away with this one 220 I had that was rated for 1.6. That 470 I have is only rated for 1.5, so it theoretically is okay. It's not getting overloaded, but it doesn't overheat either. It's working good. It's working good for this application. I think because it's so low inductance, it's not generating that hard a magnetic field, so it's being a little bit more forgiving. Now for inductor, I use this tome of knowledge from Worth Electronics. It's called A Practical Guide for the Selection of Power Inductors for DC-DC Converters. And it basically gives you the math here on how to calculate what inductor value you need. And they're a little bit cryptic. I guess you already need a bit of engineering degree to understand this, but it's actually really freaking simple math. 0.3 is your ripple voltage that you want. Then you have your output amperage, your frequency in hertz, so that would be 100,000. And then you have like U in max, UD, U out, U. I don't know why they used U. Maybe because they didn't want this to say VD and have people think about dirty things. That U is a V. Voltage in, voltage out, voltage drop or voltage difference, voltage in, voltage drop, ripple, multiplier, amperage, and that's for the step down and the step up. And it's pretty good. I punch numbers through that calculator and then I compare them to what the scope does with various different inductors that I might play around with. Indeed, I get the response that I want if I use the inductor it tells me to. And to make things simple, don't ask me for a copy of this unless you're on my Patreon. But you know what I like to do is I like to punch these mathematics into an Excel spreadsheet. So right here, I have it all ready to go. Ripple 0.3. My input voltage could be upwards of 8. Under load output is going to be 6.34. Tested current 1.34 amps. And my frequency is 100,000. Oh, boom, 34U. That's how I decided to use the 47. If I was using one of the LED fixtures that I'm thinking of upgrading to later, I'd maybe look at 650 milliamps. I'd need more like a 70U. And if I was using a triplet of 18650s instead of a dual of 26650s and was going to get, you know, maybe 12 volts, oh, I'd need 197 U. So boom, that's how that works. Then of course, bam, that busts out to the bulb. But then we have this little voodoo right here, and this is one of the most important parts of the circuit. This is your good old-fashioned LTV 870 opto isolator finger majigger. This is what she looks like. If you've taken apart power supplies in the past, you probably saw one of these puppers. They're like in every power supply. The 870 is one of the most popular part numbers, whether it's EVGA or a Big Rock Candy Mountain special you paid 50 bucks for. You're probably going to find one of these in there. And what it is, you got a light emitting diode and a transistor on the other side. So this is where our voltage regulation comes into play, and it's also why, if you are thinking about what I'm explaining here, we overcompensated our duty cycle. We need more duty cycle starting off with than we actually need, because this guy is going to affect the rest. So what happens is our output voltage here goes to a bias resistor as if we were running an LED. I bias this to about 10 milliamps in practice according to my math, just using Ohm's law. Pretend it's an LED. Try to set it for 10 milliamps. We would get a value about 680 ohms. I don't have that, and I tried a 560. It clamped the voltage too hard. I used a 1K. It's hitting a sweet spot. And then we have a Zener diode right here, 5.1 volts. And what happens is this LVT is going to drop about 1.2 volts. So we need a Zener that's lower than our target. So that together equals 6.3, and that's what we're getting out of this circuit. So what happens is right at this junction point here, when we reach 5.1 volts, the Zener diode starts to conduct. Lower than that, it doesn't. So that plus the voltage drop of this, once this point here, our output reaches 6.3 volts and tries to escalate itself higher, this Zener diode conducts. It fires this LED. That LED over here fires this transistor, which has a 1K resistor coupled to the input of the MOSFET driver. It overcomes the signal from this 10K. It pulls the MOSFET driver low, artificially influencing our duty cycle, and that is what regulates our voltage and holds it firm at 6.3 volts. And what's that do to our duty cycle? Well, we're gonna have our upswing, but then when we reach 6.3 volts, oh, it's gonna cut it off earlier. And it might not necessarily be on the same cycle. We might have some fast cycles. In fact, sometimes if we, just quick and dirty, it might look like this. And you might actually end up generating a subharmonic. If I pump too much voltage into this thing, it starts whining at about 6K. And it works so well. We press the button, the light turns on. It pulls 1.23 amplifiers from the batteries, but it's actually outputting 1.34 volts. And then on this meter, we're clamped 1.37. There's going to be a little bit of margin of error here. You can fine tune your voltage clamp with that resistor right there. If I decrease it a bit, I get slightly lower voltage. Now, if you were gonna build this from scratch, I don't know if I'd necessarily recommend two 26650s. You'd be better served with a triplet of 18650s. In that case, if you wanted to modify the circuit for 18650s, all you have to do is change the duty cycle pupper right there from 4.7K, and I found 47K is a good starting point. It will work. I can jack 3 batteries into this right now, and it will regulate down. It'll go slightly over to 6.4, and that's half because our feedback is working way too hard. Way too hard. We need to tame that duty cycle a bit. Then the only other thing you would have to change, as seen in the math, is the inductor. The rest should be pretty similar. So how does the solid state switch work? I know, I teased you with that one. That's the one you really want to know about. How do I get this little button to do what it does? Well, there is this circuit that I found online. It's kind of a momentary push button flip-flop switch using a couple of inverters. They're speccing out for a CD4069. I've used HC 2G14s till the cows come home. And in some cases, I've even used dual MOSFET drivers, and it works. We have a situation where, okay, it's off. So we got negative here, negative here. It's gonna be positive here because it's an inverter. And then there's gonna be negative here. And then the feedback here, this 4.7K is going to reinforce the negative signal here, it's going to clamp that pair of inverters into an off state or a low output state. But then what happens is we got high here in between them. That bleeds through this resistor, charges up this capacitor. And then what happens is when we push this button, it shoots a blast of positivity to the input here that overcomes that 4.7K, pushes the output low. That low pushes this output high, and then that feedback latches the whole circuit high and it turns on. Meanwhile, if we're still holding the push button, the low signal coming off this 220 isn't enough to overcome the clamping coming off the 4.7, so we can hold the button and it's not going to change, it's not going to oscillate. And then consequently, while it's on, we have low here making the top of the capacitor low. This capacitor is completely discharged, it does nothing. And then when we push the button, a blast of high gets pulled through, charging up the capacitor. It pulls this gate low for that split second, tricking this into thinking it's low, which pushes this high, which pushes this low, and then the feedback latches it as such. It is a brilliant little circuit, and I loved it, and I made it even brillianter right here, because what we got going on, the same situation, you can actually screw around with these values. Like I'm using a 100K, I'm using a 10K feedback, but the thing is, I'm only using one inverter and a Mosfet. Fancy that. Same functionality. Because a Mosfet's input control is directly in proportional to its output, in this case a P channel is going to take a negative input and turn it into a positive output, we can use the output of this Mosfet to latch the inverter. And then this circuit that triggers the Mosfet functions mostly independent of the second stage, so this circuit doesn't care that that's not another inverter, and it works identically. The only thing is, I had to, in this circumstance, beef up my capacitance to 1 UF. If you can't get this to work, you gotta play with some of these values. I've seen some inverters need more clamping force, more feedback here, as in a lower value. In this case, I needed more UF to get this to work. And then you're probably asking, well, what happened about the low clamp? You know, we have this gets latched low because this low output's here. A Mosfet only is either on or Z. It's either on or it does nothing. How do you get a low signal from a P-channel Mosfet? Well, that's easy, because this circuit is a virtual resistor to ground. It's putting a load here, so when this thing is turned off, this feedback is detecting, you know, the impedance to ground. It's as simple as that. Yada, yada, yada. I think you get the point. But it takes this circuit and makes it even more useful, because instead of needing to do this to control load, we could control load directly by just coupling it with a Mosfet, and we can control quite a lot of load. A light bulb like this is not a problem. Whatever the Mosfet's rated for, bud, you're good to go. So, after explaining this for what is turning into too long a video, do we do a part 2? Yeah, just in case, stay tuned. I'm gonna build on this and show you the finished project. Unless I don't want to do a 2-part video. I don't know. I haven't cut this up. You're talking that long, and it's just kind of like, how do I cut that shorter and still make a palatable sized video?